today? Okay, we are doing the chi-square goodness of fit test. So I'm going to give you a brief rundown of what the chi-square distribution looks like, and then we're going to run through some inference testing. Again, like I just said, it's very, very similar to what we did with our one proportion tests and two proportion tests. We're not doing confidence intervals. We are only going to be do hypothesis testing. So it's going to be phantoms. The only thing that's really missing is the p. We're not going to be defining a parameter, and I'll kind of explain why in just a second. So, some facts about the chi-square distribution. Often in the multiple choice portion of the exam, they like to ask you what are some differences between a normal distribution or a z-score distribution and a chi-square distribution. Well, the big deal and the big difference is there's not just one. There's going to be a family of distributions when it comes to chi-square. And this family of distributions is dependent on something we call degrees of freedom. And the degrees of freedom are going to vary depending on what test you are performing. So we have a different calculation for each tests that we do. So we do 3 tests total in the chi-square realm. Each one has a different way of calculating the degrees of freedom. So, with that being said, we are going to have some features that are always going to be there no matter what degree of freedom you have. The first one is going to be that they're always going to be right skewed. It's always going to be a right skewed distribution. Remember, when we're looking at distributions and we want to know the shape, you're always going to look at where is the tail. So in our case, our tail is here on the right hand side of our graph, meaning it's going to be right skewed. Some features to remember about a right skewed distribution is that the mean is always going to be greater than the median. And the median is also going to be pretty much equivalent to the peak. So it's going to be on that in that same range of values. The peak is going to be almost the same as the median. And the reason why the mean is greater is because, remember, we brought it back to like test scores. If I had a person making hundreds and fives and hundreds and tens, then that higher grade is going to bring everybody's grade up. So that's why the mean ends up being greater than the median. Now, another thing is our chi-squared values can never be negative. So every time you are calculating chi-squared, it should always be a positive value. And the reason why this occurs is because we do work with the differences between what's expected and what we observe. And when we calculate those differences, which we'll see in the formula in just a second, we always end up squaring them. That's why it's called chi-squared, because the differences between that data eventually just cancels each other out and becomes zero, and it's not useful to us. So that's why we square it. And another thing to note about the distribution, as degrees of freedom increases, we're going to become less skewed and larger chi-squared values become more probable. As you can tell, I have 3 examples for what a degree of freedom could be. We have 1, we have 4, and we have 8. If we look at our degree of freedom 1 curve, it has a really, really high peak. We can't even see it. And then as we get down to degree of freedom of 4, our peak starts to flatten a little bit. However, these higher values are less probable for chi-squared. Once we get to degree of freedom of 8, I can see that my curve is widened a lot, and I do have a lot of area under the curve over here in my higher values. So as degree of freedom increases, we do get that more area out here in the higher tail end. And one last thing to discuss, the mean of the chi-square distribution is equal to the degree of freedom. So if I'm looking at, say, for instance, my degree of freedom of 8, the mean of this distribution is going to be 8. And it makes sense because it's not going to be where the peak is, because that's going to be the kind of the mode, the most frequent values that we see. But remember, when I have a right skewed graph, it pulls the mean in that direction. So that's why my mean is a little bit to the right of my peak of my curve. And then we have the mode, which is going to be that peak is equal to the degree of freedom minus 2. So my degree of freedom was 8. So my peak is typically going to be 2 less than my mean, which in this case is 6, which seems to be about reasonable. That's where our peak is located. Now, in the AP setting, I would imagine they would just ask you questions about the distribution. I believe we've seen questions where they've done those. Here's three things. Which of these apply to a chi-square distribution? Big things to remember. It's right skewed. Chi-squared can never be negative. As degree of freedom increases, we're going to get more area in that upper tail. Those are the things they like to ask about, especially when it comes to just describing what a chi-square distribution looks like. Also, one other thing they do like to test, if you know, is there one chi-square distribution or are there many? There are many. It's going to be dependent on how many degrees of freedom that you have. Now, this is the general distribution we're going to use for our three tests. The first test we're going to talk about today is the goodness of fit test. And a goodness of fit test tries to look at counts and see if they match the distribution predicted by a model. So we're trying to see, I have this idea. I have a person who has a theory of what my proportion should be, and I want to see when I actually collect this data, does it really apply? Does their claim hold true? So we are looking at only one categorical variable and we are looking at it in one population. And a lot of these tests will end up looking similar, but you have to kind of pay attention to what am I looking at? Where am I looking at it from? So I kind of like to summarize this as one categorical variable across one population. That is the easiest way to identify a goodness of fit test. Another giveaway, especially in comparison to the other two, these tests are going to solely use one-way tables, meaning I'm going to have one row, multiple columns, or multiple columns or let's flip that, one column, multiple rows. So it's just going to be one population across many categories. One categorical variable broken down into many categories. Biggest giveaway, one-way table. The other two tests will deal with two-way tables. So this is usually the easier one to identify because it's kind of obvious based on the data that they give you. Now, with this testing, we are going to go through steps of phantoms. We, again, are just eliminating the P. So one of the first things we want to do is state the hypotheses. And the null is going to be the statement that the claim is true and the variable does have the specified distribution. Now, the unfortunate thing about chi-square testing, because we're not defining a parameter, because we don't have one particular thing we are looking at specifically, like we do with one proportion and two proportion z tests, we don't have like a general, this is how you should write your hypothesis every single time. So I do have a general idea of what it should look like, but it's going to vary from problem to problem, depending on what they want to know. So I like to write the distribution fits the claim or the distribution does not fit the claim. Now, again, you're going to want to add some context in here, but this is kind of where you should be headed. This is the direction. I am going to make a note just so that we don't forget. Add context, describe the population. What are they asking about? The marbles, the color of the marbles fits the claim, the color of the marbles does not fit the claim. Something along those lines where you are actually describing what you are testing. And just know that the wording is going to vary. Sometimes we use different terminology, like if we want to say they're all equal, we say it's uniform. which we'll use in one of our examples today, but it's not as nice as when we do hypothesis testing and it's always like it's P is this, P is not that. It's words. So I'm going to give you a second to write this down or type it. Now, we will be checking conditions, and this is going to be where we finally start differing from those three conditions that we checked for z tests and z intervals. Um, Not entirely. We're going to do two that are the same. I guess it's kind of similar to what we did with z tests and z intervals. The third one is always the different one. So, first, I do have all of the language for the assumptions and conditions. With what we do and how we've done z tests and z intervals, we really are only looking at three things. We check the conditions. We don't necessarily go in and say, this is the independence assumption, this is the sample size assumption. We just state, this is the condition. I've checked it. We move on. Now, there is one thing you always want to verify before you even get started and before you even start doing hypotheses or anything. That's why I don't necessarily consider it a condition because it's not something that AP checks for. You do want to make sure that your data is counts. Now, if you have anything like a measurement or a time or a length of time or anything that is not there are 5 people in this group, there are 6 people in this group, 7 people voted yes, 10 people voted no. If you have anything other than counts, you cannot do a chi-square test. It has to be counts. It has to be putting people into categories. It has to be categorical data. It cannot be quantitative. That is just your first check overall. It's not something you have to write down. It's not something that's a part of the written assumptions and conditions. It's just something you need to be doing before you even get started. So once you've verified that you've done counts and that you are doing chi-square testing, that's when you get into writing your hypotheses, checking the remaining conditions. And two of the conditions are the same. We are checking, is it random? And we are checking the 10% condition. So basically, if I take my sample size and I multiply it by 10, can I assume that my population is larger than that? And then the one thing that's going to be different is the expected cell frequency condition. This is what I usually call expected counts condition. And that's just going to make sure that you have at least 5 individuals in each cell. So at least 5 people, expected counts fall into each category. And one thing that's really important to note, the College Board grading rubric requires that you actually list the expected counts. You can't look at it in your calculator, you can't do all the multiplication on on your calculator and leave it there and say, "Oh yeah, they're all bigger than 5." You have to write it down. Otherwise, they do not give you credit for this condition. It has to be listed, which is what we'll do in our general run through of the test, but make sure that you do not forget it. Oftentimes, I will get a lot of students who still just write all expected counts are greater than or equal to 5. Great. Where are they? Where are the counts? You have to support your claim. Otherwise, you do not get credit for that condition. Now, the calculation is intense. It's one of those summation formulas, which oftentimes is not too troublesome, especially when you only have 2 or 3, maybe 4 categories, but it's extensive. It requires us to take the summation of the observed count, so the count that we actually have in our data table, the expected count, which you have to calculate, square that, divide it by the expected count, add it to the next category. add it to the next category. Now, it is time consuming. So, what I'm going to show you today is going to rely solely on the calculator doing this for you. The formula still works. It still is something where we can take all of our observed values, our expected values, plug them in, add them together. We're going to get the same summation. It's just it's time consuming, and I think that this is one of the tests where it's easier to just go the route of the calculator. So again, observed counts are what you actually see in your table or in your data. The expected counts are often calculated by taking your sample size and whatever the null proportion is, it I've tried to turn it into a formula here, but oftentimes it's just like there's equal distribution. Well, what you would do in that case is just take your sample size and divide it among your categories. If you expect the same amount of people in each category, that's how we get that. So, one other thing before we get to the actual calculator steps, degree of freedom for the chi-square goodness of fit test. You're going to take the number of categories and subtract 1. This is very, very important because your calculator is going to ask you how many degrees of freedom do you have. This is big key idea. And this is one of the big things that differs from test to test, how the degrees of freedom is calculated. So make sure you know that for goodness of fit tests, we're going to take our number of categories and we are going to subtract 1 from them. Now, calculator steps I will run through with you when we're actually performing the test in just a second. So we will get back to this. But again, it's going to be in that stat tests menu. But with this particular type of testing, we do have to enter data into a table. So we will put our observed values into L1, our expected values into L2, run the test, and we should get out our chi-squared value and our p-value. Now, the summary, the conclusion is exactly the same as it was for inference testing with one proportions, two proportions, z tests. Now, the only thing that kind of gets changed is we are going to be talking about, usually this says the parameter in context. We do state the alternative hypothesis in context. And for my English people, this is one of the things that bothers us the most. And trust me, I've researched it. I've looked at many, many different AP exams, different textbooks. This is one of the cases where we often write double negatives. And if it bothers you, I'm so sorry. But I've looked at AP exams and they've had double negatives in their answer choices. And I've looked at textbooks and they write it as double negatives because your conclusion should be describing the alternative hypothesis. And our alternative hypothesis is typically it does not fit. And so when we fail to reject that, it it ends up being double negative. I just want to warn you, my English people, I'm thinking of you as we move on. Okay, let's just go ahead and do one of these tests together. Mr. Choate wants to offer students new types of food in the cafeteria next quarter. He wants to know if each type of food will be equally popular so he can prepare the cafeteria for next quarter. He takes an SRS of 100 students and asks them which of the new items they prefer. So we have a table, and I see that I have one row with multiple columns. So right away, that's a signal that I should be doing a goodness of fit test because I don't have a two-way table. And does the data provide convincing evidence at the alpha equals zero point zero 0.05 significance level that the food preferences are not equally popular? So we are doing a hypothesis testing. Again, it's going to follow phantoms, but without the P. So we're doing phantoms today. So first thing we want to do is write out our hypotheses. So I have verified that these are counts. This is not quantitative data. This is 20 people who selected pad thai, 24 who selected tacos. I'm not doing any type of measurement. That's my first check. Now that that's okay, I'm going to go in and write my hypotheses. So I wrote this in two different ways. And the reason why I did this in two different ways is because I do want to introduce you to uniform. Uniform just means that they're the same across the board. So sometimes in the AP test, they will use uniform. Sometimes they'll say equally likely. I just want you to see both before you get there and you're like, I don't even know what that means. So the food preferences fit a uniform distribution, or you could write the food preferences occur with equal frequencies. Now, you only have to pick one, you don't have to do both. Now, for the alternative, we just say that they do not fit a uniform distribution or they do not occur with equal frequencies. Either one is okay as long as you pick the matching pair, either write about uniform distribution or write about equal frequencies. And this is the only one where I wrote it in both ways, but I did want to introduce you to that term. And I generally like to try to fit in the fit and does not fit into my hypotheses so that I can kind of reiterate to myself that I am doing a goodness of fit test. So once I've written out my hypotheses, I am going to check my assumptions and conditions. First two are things that we should be familiar with. We're doing an SRS. It was stated. That checks off my random condition. The next thing I want to check is 10%. And I took a sample, or Mr. Choate took a sample of 100 students. And we can assume that there are at least 1,000 students in the population. That seems reasonable. At least 1,000 students in a school. Not something that I would necessarily argue against. Now, the third condition is our expected counts condition. So this is where we have to go in and look at what the claim is. Mr. Choate wants to see if they're equally popular. And so we have to list out these expected values for each category. So what I like to do, especially because AP is so particular about this, I basically copy the table that I am given, or I set up a table similar to what data I have. So I have the type of food: pad thai, tacos, pizza, cheeseburgers. I have my expected counts are going to go into the boxes. And this is going to take care of that necessary listing of the expected counts. Now, you don't have to draw out a formal table on your AP test, but do make sure that you list them somehow, some way. So for expected counts, if I had 100 students surveyed and I have four categories, if I expected it to be equally popular for each food category, then I would expect to see 25 students in each category. So 25 students liked pad thai, 25 students liked pizza, 25 students liked cheeseburgers. And then I can state all expected counts are greater than or equal to 5. So just somewhere on your paper, expected counts: pad thai 25, tacos 25, pizza 25, cheeseburgers 25. It could be a list. It does not have to be a table. I just put it in a table format because generally they're giving you a table format anyway, and I follow along with that, just plugging in my expected values. And once you have confirmed that all of your conditions are met, you're going to move on and you are going to name the test. Now, for us, this is a chi-square test for goodness of fit. Yes, it is very, very important that you write out goodness of fit because you're going to have two other chi-square tests. That is going to make or break whether you can't just say chi-square test. They need to know which chi-square test are you doing. Another option that you could do here, as far as last year's grading and prior to the crazy AP exam we took, you can abbreviate goodness of fit as GOF. That is commonly accepted. You can do that perfectly fine, at least as far as previous AP exams have gone. Chi-square test for GOF instead of goodness of fit written out. So we have all of the work leading up to the test statistic. Now we have to actually go in and calculate the chi-squared value and the p-value. Now again, you could go through the summation formula. I do think it's a little time consuming, so this is one where I go straight to the calculator. First thing you have to know is degree of freedom. Degree of freedom is our number of categories minus 1. So I have 1, 2, 3, 4 categories. So my degree of freedom for this test should be, oops, not that, 3. Now I'm going to open up my calculator and I'm going to share it with you guys. So let's make that fit. Okay. We are going to first enter our data into our calculator. So we're going to go to Stat, Edit, Edit, and then in L1, I'm going to put my observed values. So I have 20, 24, 35, and 21. Okay. I usually pre-enter this data. And then in my L2, I'm going to put my expected values. So we said we should expect 25 in each group. And one thing, if you are dealing with larger numbers and you don't really know, it's not something we can easily divide, you could always go in the actual edit, and type in your calculation, and it's going to turn out what you need. So I have my observed, I have my expected. The next thing I'm going to do is go to Stat, going to go over to Tests, and I'm going to go to, oops, I went too far, all the way down to D, chi-squared GOF, goodness of fit, test. This is the only chi-squared test that has his own, very special. Like I said, it's the only one dealing with one-way tables, which is why it gets to be its own. And we say observed is an L1, expected is an L2, perfect. Degree of freedom, however, is not 5, it's going to be 3. And then we're going to go down to calculate. And it's going to tell us that our chi-squared value is 5.68. Our p-value is 0.1282 or 83. And degree of freedom is 3. So the only 3 things you have to write down are the chi-squared, the p, and the degree of freedom. Don't worry about this last line. Not necessary in terms of getting full credit on the exam. So I'm going to go back to my paper. And I have chi-squared is 5.68 and p was 0.1283. And then we just conclude. Since the p-value of 0.1283 is greater than alpha, we fail to reject the null. Now this is where I warned you about double negatives. There is not convincing evidence that food preferences do not fit a uniform distribution. I know it sounds weird. I know double negatives bother some of us. It bothers me a little less each year, but the first year it really bothered me. But that's how they format it. That's how it is on the AP exam. That's how it is in textbooks. So we are just going to go with what you are most likely to see on the AP exam. So I'm going to give you about a minute or two to copy this down, and then we will move on to our last example. Okay, so I'm going to go ahead and move on. I will post the PDF of these notes at the end of the day, and I can always go back if you're missing something once the lesson is over. So, example two, the paper Linkage Studies of the Tomato reported the following data on phenotypes resulting from crossing tall cut leaf tomatoes with dwarf potato leaf tomatoes. We wish to investigate whether the following random sample of offspring is consistent with genetic laws, which state that the phenotypes should occur in the ratio 9:3:3:1. So we have our table. Again, I'm noticing that it is a one row, multiple columns, which is a one-way table, signaling probably going to be doing a goodness of fit test. Carry out a significance test at the alpha equals 0.05 level to test whether the frequencies are consistent with genetic laws. So I am going to go ahead and set up. I do see that I have counts. Frequency is counts. I don't have any quantitative data, so that's good. Now I'm going to write my hypotheses. So, first thing I have is the distribution of offspring fits genetic laws, and then I have the distribution of offspring does not fit genetic laws. So, again, fits does not fit. Add some context into it. Not always going to look exactly the same every time, but it does follow a general pattern. For our assumptions and conditions, we are going to first see if it's random. I do have a random sample of offspring. I have a total, so I went ahead and added all of our sample together, 1,611. And this is talking about plants in general, so I can assume that there are at least 16,110 potential offspring in the population, especially with how many we've got in our sample to begin with. I could assume that this number gets pretty large. So I went ahead and said the 10% condition was satisfied. Now, I did set up my table to calculate the expected counts. Now, this is not a distribution or an expected distribution where we're saying they're equal across the board. This is one where we're trying to follow a ratio of 9:3:3:1. Now, with the genetic laws, it's going to say that if I were to take my whole entire population, 9 out of the total, which is 16, that percentage of them would fall into the first category. 3 out of 16 would fall into the second category. 3 out of 16, third, 1 out of 16. And that's just proportions, not necessarily just three people. So the way I calculate expected counts for my four different categories is I'm going to take my entire sample size of 1611 and I'm going to multiply it first by 9 out of 16. And that's going to give me 906.1875. And we're just going with the ratio is presented in the order that they have presented the data. That's the only conclusion we can really draw. That's what we're going to go with. And then for my tall potatoes, it's going to be potentially 3 out of 16 times our sample size, which was 302.0625. Similarly for the dwarf cut. And for the dwarf potato, they were just 1 out of 16. And I got 16 from adding 9 plus 3 plus 3 plus 1. So 9 out of 16, 3 out of 16. Just got the ratios from that genetic law. And I got 100.6875. And the nice thing about this particular test is it does not require you round. We can type in the decimal values into our table and it's going to accept it. And again, you do have to report the values for credit on the exam. Now, you don't have to write out your formula. You don't have to include this 1611, 9 out of 16 calculation. You can just state the value, but I put it in here for the sake of notes. And you do want a statement saying all expected counts are greater than or equal to 5. Once we have finished with our expected counts, we do name the test. And again, you can say GOF, GOF, chi-square test for GOF. And we are going to jump to the calculator and enter in our data. So I'm going to open up my calculator one more time. Let's see if I can split screen this so that you guys can see both at the same time. There we go. Oops. Okay, so I'm going to go ahead and start entering in my data into my calculator. I'm going to do my observed 926, 288, 293, and 104. And I'm going to do my expected. So we said 906.1875, 302.0625. And again, if you don't want to do all of these calculations separately, you can do them in the stat edit menu. So I could do in 1611 times 1 over 16, and that's going to give me my 100.6875 value. So you can do it within that menu itself. Once I have all of my data in, I'm going to go to Stat, Tests, down to the letter D, enter. I have observed L1, observed expected L2, and I do still have 4 categories, so my degree of freedom is going to still be 3, and I'm going to calculate. And I get a chi-squared value of 1.4687 and a p-value of 0.6895, which is going to save you tons of time, especially when you have to do summation for multiple categories. And my last step is to actually go in and conclude. Since the p-value of 0.6895 is greater than alpha, we fail to reject the null. There is not convincing evidence that the offspring distribution does not fit genetic laws.